So yeah, this week we are going to discuss graphs and histograms, in particular descriptive statistics. And basically, what descriptive statistics are, we're looking at ways to represent data, right? And in particular, this week we're looking at ways to visually represent data. And we're using graphs and histograms, right? And in there's kind of sandwiched in tables, right, to visually represent data so that we can understand it a lot better. So in the first lecture, in the first week, we looked in particular about how to classify data and then how to collect data. So the question is, after we've collected all of this data, what do we do then? Right? What do we do after we collect the data? So that's where we are. We have collected data. Now what? Now what do we do? Right? And the next thing that we want to do after we collect data is we want to actually represent it. We want to represent it in some manner. So the question is, what are descriptive statistics? That's the question we're asking. And the idea is that when we collect a bunch of data, we call it raw data. We haven't processed it. We haven't done anything with it, right? So we call it raw data. It's just data that's just completely and totally raw, right? We haven't done anything with it at all. So, and when we have that raw data, it's not easily understood. So imagine, right, if we used one of those sampling methods and we weren't sampling 20 people, because if we sampled 20 people, that might be easy to just look at the raw data, glean some information from it. What if we sampled 5,000 people? Could you look at a data set of 5,000 people with 5,000 responses and be able to look at it and immediately just like pick something out and be like, this, I can glean some useful or usable information from it? No, you couldn't, because it's just too massive and our brains can't process information in that manner. And what descriptive statistics is about, descriptive statistics is about summarizing the data and organizing the data so that it can be understood easier. So those two pieces are so critical, right? The two pieces that are critical here is this idea of summarizing the data and organizing the data. And in this phase, as the name implies, we want to describe the data, but we don't want to actually make inferences, right? We want to describe the data, but not infer anything from the data. And what we mean by that is we want to stay as neutral as possible as we look at the data. So you don't want to be making a graph and start saying, oh, this must mean that, right? You don't want to do that yet. You just want to describe it and get all of your descriptions out before you say what this must mean. An example of that might be, let's say you're doing a study of school performance, kids performance at a school, right? And you start testing kids and you start seeing some low scores, right? And once you start seeing these low scores, you're like, oh, okay, I don't even need to do anything else. I know all the scores are going to be low. But you haven't actually described all of the data. You haven't summarized the data you collected. You haven't organized it. Because once you organize it and summarize it and do whatever comparisons you need to do, you might find that what you thought you were observing, just from looking at the raw data, looking at the responses as you got them, that what you thought you were observing didn't match what the data actually is representing, right? So that's why you don't want to make inferences before you describe the data. In particular, when we want to represent data visually, we want to use graphs. And graphs can do two things for us. They can show us the data itself, and then they can also show us relationships between data, right? So those two things are really important, and that's how we're going to use graphs. And the main goal when we are describing and organizing data and doing descriptive statistics is to describe some important characteristics of that data that we collected. So the important characteristics that we want to describe are the center, right? And the center is basically a representation of where the middle of the data set is, and there are different ways we can describe where the middle of a data set is, right? The variation, which is basically telling us how different data points, right, vary from one another. Are they spread out? Spread out might mean if you have a basketball team, and there how many people on a basketball team? Five starters, 5 people on the floor, or whatever. You have those 5 people on the basketball team, and one person on the team is 5'2", while the other person on the team is 7'10", right? That would be a lot of variation, wouldn't it? And everybody else was just scattered out in between. On the other hand, what if you had a basketball team where everyone was like 6'5", 6'6", 6'7", 6'5", 6'6"? There's not a lot of variation. It's not very spread out. Everyone is around the same height. So that's variation. Distribution is like the nature or the shape of the data, right? And we'll go into that a little more today, what we mean when we say the shape of data. But essentially, the idea is that data does take on a shape when we actually start to work with it visually. Data will take on a shape, and the shape that data makes tells us more about the data set itself. Like, it helps us know more about the data set. We also want to look at what we call outliers. Outliers are basically data values that are super far away from all the other data points. For example, let's say one of you all in this class was, 8 feet tall. Your height would be so far away from the rest of our heights that you would basically be an outlier. So anything that's really, really far, and there actually is a method for finding out what is an outlier, like, definitively, and we're going to go over that a little later, but that's basically what an outlier is. And then lastly, time. So data, in many cases, data will change over time. So if we're doing some kind of long-standing study, right, where a prospective study where we're studying something as it occurs, as it changes, right, that would be an example of data changing over time. An example of that would be in the spring of this year, right, I gave the students an assignment. This was in March. So I actually gave them the assignment before everything shut down. And the assignment was basically to look on one of the web trackers and, do some data analysis with the numbers for COVID-19 cases. That was the assignment. Do some analysis on the COVID-19 cases. And what the students found was that, and they kind of found it accidentally, they would go in one day, right? They had to look at the top 10 states, look at how many people had died from COVID-19 in the top 10, not states, top 10 countries in the world, right? How many people had died, how many people had survived, how many people still had it. Just those 3 numbers, that's what they had to look at. But what they found is if they took the numbers from 2 of the countries on one day and then they went back in to try to get more information, the numbers from those countries they took would have changed by the time they got back into the system, right? So each day they were finding that the numbers were changing, right? And that is an example of just data changing over time. So anything that's not static is going to change over time. Now, with each of these, we actually kind of get something interesting because we can make a little, what's it called, acronym for this, which is C, or is it an anagram? I can't. I think it's an acronym. Don't quote me. CVDOT, right? And that's what we get. CVDOT. So CVDOT is what you are going to use to remember those important characteristics: center, variation, the distribution, outliers, and time. When I say describe a data set, right? When I say describe a data set, what I want you to describe is all of these characteristics of that data. That's what you should do when you describe a data set. You should comment on the center, comment on the variation, comment on the distribution, what kind of distribution it is, find and identify any outliers, and also comment on how that data is going to change or is changing over time. In many cases, the time one might not show up as prevalent because we will look at a lot of static data sets, right? So the time piece usually won't show up, but the other ones will show up. So we're looking at the center, variation, distribution, and outliers. So when we talk about data, in particular, this time we're starting off talking about how to visually represent data. And we're going to begin our conversation on how to visually represent qualitative data. So there are three main tools that we use to represent qualitative data. And remember, qualitative data is the data that's numbers, not numbers. Qualitative data is the data that's categories, right? Words usually. So how do we visually represent qualitative data? We use graphs, tables, or we can use charts. So an example of a table we can use to visually represent qualitative data is a contingency table. And basically a contingency table is a table that summarizes, right, what's happening with two different qualitative variables or two different categorical variables. Categorical, qualitative, you can use either one, right? And that's a contingency table. So here's an example of a contingency table. This is a study that came from one of the textbooks, but basically this study was done with college students, and it showed the distribution of student genders and whether or not they were looking for a spouse while they were in college, right? And the idea is we're comparing two data variables. One qualitative variable is the student's gender, and the other qualitative variable is whether or not they're looking for a spouse. So those are the two qualitative data variables. So in the gender side, we had male and female. Those are the responses we got. And for looking for a spouse, we got yes or no as the responses. And what this is doing, this is summarizing how many people did each one. So the way we would read this is the female column goes straight across like this. This is the female column. And if we just look at this row right here, we just look at this one row. I said column, but I meant row. Looking at this one row, we can get information about all of the respondents that said they were female. So female, looking for a spouse, no. How many people said no? How many female respondents said no, they're not looking for a spouse? 86 of them. How many female respondents said yes, they are looking for a spouse? 51 of them. And how many female respondents were there in total? 137. And for the male respondents, we have 52 said no, 18 said yes, and 70 in total. So, and then here we have the total numbers. If we wanted to say, well, let's look at who said no, we could look at this column right here. And these are the people who said no. How many of the people who said no were female? 86. How many were male? 52. And in this column, how many said yes? 51 were female, 18 were male. See how it's yes, this one intersects with female here, right? That's why it's 51 said yes that were female, and 18 said yes that were male, for a total of 69. And this 207 in the corner is how many there were in total. So that's a contingency table. We'll use contingency tables from time to time when we have two different data variables where we want to kind of show the relationship between those two data variables and how they change relative to each other. So moving on, the next way we can visually represent qualitative data is using what we call a bar plot. So a bar plot is basically a way to represent a single qualitative data variable, right? And we have another kind of bar plot which is called a relative frequency bar plot, where basically we're showing percentages instead of the actual numbers. Anytime you see that relative frequency word, you're showing percentages and not the actual numbers. So here's an example here. In the first one, this is counting how many female respondents there were, and this is counting how many male respondents there were. So here you can see that's how many male respondents there were, and this is how many female respondents there were. And for the relative frequency one, you see how it's decimals here? Because it's showing the percentages. That's what it's showing on the relative frequency one. It's showing percentages. So we're actually going to skip past this one here. We're going to go to the next one. We're going to skip past that slide and go to the next one. We'll come back to this kind of example, but we're going to skip past that one because I want to focus just on this visual representation aspect. So when we have a bar plot with two different variables, which we can have, you can have what you call a stacked bar plot, right? Which is basically like a contingency table, but you're stacking the responses, right? We can have a side-by-side one, which is basically you put the different responses next to each other instead of on top of each other. And then you can have a standardized stacked one, which is like a stacked one, but it's percentages. So here's the name. No, we don't have an example here, but I'll draw an example. So let's say I asked you all, I asked a bunch of students who likes chocolate, who doesn't like chocolate. So I can go down here. I could say maybe I tried to split it down between gender like this other one, right? And that'll be gender. And then I'll do the count up at the top for who likes chocolate, who doesn't. And here, if I have male, I could go up to here, and this section would be yes. And then this section that's stacked on top of it would be no. And then the total is how many there were in total. So that would be like stacking it. So it's like we're measuring both things, but we're stacking it because we're sorting it by this whole category of gender, right? It's not as complicated as it may seem. It's actually relatively simple. And for most of these, we'll be using Excel to make these different graphs and bar plots and whatnot, right? We'll be using Excel for it. Here's another example. This is a pie chart. Basically, a pie chart is exactly what it seems like. You probably all have seen pie charts before. And a pie chart basically is when you have a circle and you split it so that each portion of the circle represents the actual amount of the thing that fits into that circle, right? So here we have a pie chart that represents stolen boats, right? We have a pie chart that represents stolen boats, and just from looking at it, what kind of boat was the most stolen?
Jet boat.
Just jet ski.
The jet ski. Right? And we know it's the jet skis because the jet skis is the largest portion of the pie, right? So we know it's the jet ski. So each of these portions represents the actual amount or the proportional amount of that thing. So that's visually representing qualitative data. It's very straightforward. A couple of different things that we do. Usually, if you have some qualitative data and you want to visually represent it, you want to jump straight to either a bar plot, right? Either a bar plot or to some kind of pie chart. That's just the easiest thing to jump to. You got some qualitative data, make a bar plot, make a table, or make a pie chart. Right, let's just keeping it simple. So next, what we're going to discuss visually representing quantitative data, which is like numbers and stuff like that. That's quantitative data. And in particular, we're using plots, graphs, and histograms. So starting off, we have a scatter plot. And with a scatter plot, the only time we actually use a scatter plot is when we have two different data variables and we are trying to compare them together, right? So let me draw a little example. So it's kind of hard to see this example, but you can see it when you look closer in the slides, and we are going to talk about that in a second. Let's say we were trying to look at foot size and let's say shirt size, right? Foot size and shirts. Maybe we need to say something else. We'll say foot size and we'll say height, right? Because shirt size might not be numbers. At least for me, shirt size is like medium, small, and large, that kind of thing. So we'll say foot size and height instead. Well, let's say we measure someone and we get that their foot size is a size 9. Right? And then their height is, let's say, 65 inches. Basically, we put a dot right there for that person because we matched their foot size with their height. Right? And then what we end up getting is we'll get dots as we measure other people, dots that represent all these other different people. And then we can look at those dots and see if there's any kind of pattern. So for example, here it kind of looks like as the foot size gets bigger, right, the height is also getting bigger. So that would be just an example. In this example over here, they're actually measuring life expectancy with total fertility. So this was something I got from, I forget what source I got it from, but it was from some article somewhere. And they were comparing life expectancy with how many children there were per family, right? And what they found is that, and they continuously find this, is that in places where you have a lower life expectancy, right, you actually have more children in each family, right? That's what they found. And they always have all these theories about why people with lower life expectancies tend to have more children. One of the theories I've heard is that when you have a lower life expectancy, they say it's like more children to replace children that may perish. I personally don't know about that one, but that's just like kind of the evolutionary standpoint, like that Darwin kind of standpoint. One of my students a couple of years ago said something I thought was very profound. They said that their theory was that places that have a shorter life expectancy tend to have a culture, right? Tend to have a culture that more values family. Tend to have a culture that more values family, and that is what makes them have more children. And it's not actually the lower life expectancy, it's the culture you find in places that have lower life expectancies. So places that tend to have lower life expectancies might be, places where there's a lot of war. These things destabilize regions and stuff like that. And where are the places that have a lot of war? Europe hasn't had a whole bunch of war and stuff, but there's a lot of conflict going on in Northern Africa, for example, right? But the culture in Northern Africa is one that values having children. That's one of the core values of having children, right? Other places where they categorize them as being particularly dangerous. So maybe some places in South America or something, right? I'm going to say, quote unquote, the developing world. These are places where there's a lot of destabilization, and these places are also more likely, their cultures are more likely to value having children. So question, with this example, that student introduced a new variable, right, that we had not considered when we just made this chart. What kind of variable would that be? Anybody remember what that would be called? Or what kind of variable? Anybody remember? Starts with a C. So I'll tell you, it's a confounding. Oh, you were going to say something, Danita? Go ahead.
No, that's okay. I was going to say I would have been wrong.
Okay.
I would have been wrong.
So it's a confounding variable in that it's something in the middle that we didn't really consider. Right? So that's what that would be, a confounding variable. So we're going to move to the next one. So again, we're talking about visually representing quantitative numbers, number data. Another way we can do it is with what we call a dot plot and a mean. So the dot plot is basically where you just have a number line, you collect information, you put a dot where the number falls. So this would be like collecting GPAs, and they put dots where all of their numbers fall. We could do a dot plot. We could do a dot plot with heights. So let's say we had heights. I'm gonna put 65 inches in the middle. Then I'll say maybe 62 inches. And then I'll say maybe 69 inches. So where do you all fall? On the dot plot, where do you all fall? So give me your height. So we'll just start off. You can give your height, and you can say where you fall on that dot plot. Where do you fit? So anybody want to start? Nakia, how tall are you?
Y had to be the first one, probably the shortest. I don't see mine on there, but 5'4".
5'4", yeah, 5'4" would be 64 inches.
So it'll be the smallest one represented.
Nope, you'd be right here. So that's a dot for Nakia. Danita, how tall are you?
Okay.
5'7".
5'7", so that'd be a dot over here for Danita, right? Chanel, what about you? How tall are you?
Same, 5'7".
So in a regular dot plot, what we would do is we would put another dot right here. That's why I'm just kind of making this dot a little bigger. But you overlay the dots in a regular dot plot. Anne Marie, how tall are you?
What am I? 6'4", 5'4", something.
5'4"? Okay.
Yeah.
So that would make this dot a little bigger. Hermila, what about you? How tall are you?
I am 5'4".
5'4"?
Yes.
That would be another dot right here. That 5'4" dot is getting bigger. Usually it gets just darker. Like if you look on the screen up above, it's just getting darker. But I can't do that. Ashley, how tall are you?
5'1".
5'1", so that'd be a dot down here.
And 3/4.
Brenda, what about you?
5'2".
5'2", so that would be a dot right here. Ebony?
5'7".
5'7", that'd be another dot right here. Samrari, how tall are you?
5'2".
5'2", a little bigger dot here. Fabian?
5'2".
5'2"?
Yeah.
Another dot right here. Shantae, I'm sorry. Shantae?
5'4".
5'4". Ooh, all of y'all are 5'4". This dot's getting bigger. Gloria, how tall are you?
65 inches.
5?
65 inches.
Okay, so you'd be a dot right here. So basically that's a dot plot. We collected the data, we put the number on the number line. Dot plots are good because they show us where the middle is. So where would you all guess the middle of this data set is? Like where would you guess? Where do you think that, imagine if this was like some kind of uneven piece of wood or something, right? And where the dots are bigger, that's where like it's a little heavier there. Where would you put your finger to balance it? Maybe like somewhere around where? Anyway?
Like 67? Maybe
Up here? You think that would balance it?
No, like 60.
64.
64, cross that out. 64. 64 is a good guess because there were a whole bunch of you all that were 5'4", right? So that's kind of like the middle of the data set or the average. So we can get kind of an estimate by looking at the dot plot of seeing where the center of the data set is. So dot plots are very useful. Now, the mean is like the mathematical average, and that's basically when you add up all of the numbers and divide by how many numbers there are. This formula here is essentially just the formula for the mean. That's all that is, right? These are all of the numbers. See, we're adding them all up, and then we're dividing. N is how many there were. We're dividing it by n. There are two different ways to say the mean. We can say x bar, or we can say mu. X bar is when we find the mean of a sample. And the reason why it's X bar is because there is a little bar at the top of the X. See the little bar on top of the X? That's why we say X bar. And the reason why we say mu is just because that is a Greek letter and it's called mu. It looks kind of like a U with two lines or an M. The way you should draw it is you should draw a U and then draw another line. That's the best way to draw a mu, right? So one is the mean of a sample and the other is the mean of a population, right? That's what it is. And this is kind of a sneak peek into what we'll do later, but the mean of a sample gives us an estimate about what the mean of the population would be. That's what it does. It gives us an estimate. But we'll come back to that later. We'll talk about that a little more later. but just an idea of what's going on. We're getting that sample information. We're going to use it as an estimate for the population information. So here is what we call a stacked dot plot. So when we go back to this dot plot, what would have made more sense? So like all these people that were at 5-4, what is there anything you all can think of that would have made more sense over just making that those dots really, really big? Is there something else you could think of that we could do?
Stacking them.
Stacking them, yeah. So like we could do 5-4, and then there's another 5-4 person, we put them on top. Another 5-4 person, we put it on top. Another 5-4 person, we put it on top. That's a stacked dot plot, right? Where instead of overlaying it, you just stack it as you get more. And what that lets you do is it lets you get an even better representation of where the middle of a data set is. So in this case, it's a little bit easier to see where like the data is clumping or centered around. And we can see that the data is kind of clumping around here. Like this is kind of where we want to balance our finger if we want to balance ourselves on the data set. Like there's an equal amount of stuff over here on this side of that line as over here. Like the same number of people on this side as on this side. So that's why it would balance in the middle. So this is what a stacked dot plot is. So the other thing that we're going to talk about really, really briefly, and I'm actually going to show you this by showing you an actual example first, because there's a lot of text and sometimes it can get easy to get lost in the text. So we're going to get the framework of what we're trying to find, and then we're going to go back and look at the actual thing. So if we look here, this is what we call a frequency distribution table, right? And a frequency distribution table is essentially a way of counting how many things are in a particular category and sorting them. So this upper bound and the lower bound, that's basically what makes our category. So another way we could write this is 49.5 to 59.5, right? We could do it like that. Or this would basically be like 49 to 59, right? And then we have 59 to 69, that kind of thing, right? So that's why it's like that. And basically all we're doing is we're saying how many people were in that category, and that's what makes it a frequency distribution. Or basically how frequent does somebody appear in that category. And once we have somebody that appears in that category, we just add a number to that box. So how many people on this calculus test scored between a 69.5 and a 79.5? How many people does it look like? You're on mute, Chanel.
Is it 30? You said 69 to 79?
Yeah, it's 30 right here. 30. So it's 30 because that's the frequency for this category. How many people scored from 89 to 99?
15.
15, exactly. So it's very easy to read. And when you do it like this, all the other text kind of is like, well, why do we have all this text to explain something so simple? You split it into categories and you count how many people are in each category. The only thing is you got to be just a little careful about how you're splitting it into these categories, right? You just got to be a little careful about it. Now, the cumulative frequency, on the other hand, right? The cumulative frequency is how many people are in that category and all of the categories that are below it, right? So, for example, 5 people scored from 59 to 69. But 15 people scored in this category and in this category. And how did we get that? We got that by adding the two categories together. See, we added 10 plus 5. And how many people scored in all 3 of these categories above? Right? 30 plus 10 plus 5, which is 45. So cumulative frequency is just adding all of the people in all of the categories up, right? But it's just the categories that are below it, right? And so how many people were there in total? Anybody can see how many people were in the class in total? Somebody say it.
100.
100, because there were only these categories. These are all of the categories. So whatever number this number is going to be the people in this category plus everyone above. Right? So that's 15 plus 40 plus 30 plus 10 plus 5, which is everyone. Right? The last kind of frequency distribution table that we can have is what we call a relative frequency distribution table. And the idea there is just that instead of using the actual number, we're using the percentage. So how many people did we say there were in total? We said there were 100 people in total. So for this category here, what percent of the people in total were in this category? Well, that would be 5 over 100, which equals what? 1/20th, which is 0.05 or 5%. That's 100, so it's kind of really easy. So for the next one would be 10 over 100, which equals 10%. And then 30 over 100, which equals 30%. And then we have 40 over 100, which is 40%. Then we have 15 over 100, which is 15%. That's the only thing we need to do to make it relative frequency instead of just frequency. Relative, anytime you see that word relative, you're thinking percentages, right? Anytime you see the word relative. So the other tool that we have is called a histogram, and that's another tool for visually representing quantitative data or number data. And a histogram is like the most important tool that we can use. We're going to use histograms over and over and over again. Basically, a histogram is like a dot plot, but instead of using dots, we're using bars, and we make the bar for that category a little bit bigger as we add people to that. So histograms are also very useful because they give us the clue into how to describe the shape of a data distribution, right? It gives us a clue for how to describe the shape. And one other thing that's important with a histogram, we have to be careful of what we call the bin width. So a histogram is basically like doing this, but in graphical form. So like we could say 49, 59, 69, I'll stop at 79. And then how many people? Let's go 5, let's go 10, 20, 30, 40. And how many people were from 49 to 59? Let's look back up here. How many people? 5. So we're going to draw a little bar here that goes up to 5. It's kind of supposed to go up to 5. I know it doesn't really. And how many people were from 59 to 69? 10. So
10.
10. So we're going to draw another bar here that goes up to 10. And for 69 to 79, how many people were there?
30.
30.
30.
We're going to draw a bar that goes up to 30, right? And we would do the same thing for all of the other categories, right? I just stopped there, but that's basically what a histogram is, right? We're putting people into each of these bins, and as we put people into the bin or their section, right, their stack gets a little higher. It's like a dot plot mixed with a frequency distribution table. It's like a mixture of the two things, right? So, and bin width describes basically how large that section is. So in the last example we had, we could go from 49 to 59, or we could go from 49 to 50, right? Or we could go from 49 to 52, and maybe that's our category. Or we could go from 49 to 54. We go up by 5 instead of going up by 10, right? So that's the bin width. How big is the category that we're looking at? And we're going to see an example to see why that's so important. So here's an example of a histogram, right? We're measuring the number of extracurricular hours that someone spends on, it's the number of hours someone spends on an extracurricular activity each week. And basically we're just dropping them in bins. So it looks like 150 people were between 0 and 10. Maybe that's like 25 people were between 10 and 20. Between 20 and 30 is about like what? Maybe that's 5. Maybe 10. And then from 30 to 40 is like 2. From 40 to 50 is maybe like 1. I don't know, 1 or 2. And the rest of these are like 1 or 2. Right? And now looking at the bin width or how large that is, again, we could have measured this from 0 to 10, or we could measure it from any number we want. We could go from 0 to 5 and measure it like that. So let's look at some scenarios and see which of these things do you think are better than other ones. So let's look at the first one. They did bins that go from what to what. They counted how many people had extracurricular hours between 0 and 50. This first one, is this useful?
No.
No.
It's not useful at all.
No.
Because it just obscures all of the information, because it's kind of useful to see these smaller categories. What about this one? How's this one look? Does this look useful? We went in categories of 10 hours. Definitely better than the first one, right? It's definitely
It's just
Yeah.
better than the
this
first one.
part is a little hard.
Or yeah.
So far down, you can't really distinguish what.
What's
those
going
numbers.
on down here?
Yeah.
Gotcha. And what about this one? This one's not bad either, right? This one's
No.
going with sizes from 0 to 5, and then from 5 to 10, and 10 to 15. That's not
That's
bad.
better.
And then this last one, what do y'all think about this last one?
It's
Yeah.
not bad. It's just broken down into like smaller units, I guess.
But what you can see is like, see how here in this one and in this one we get like a more defined trend, right? It's easier to see the trend. And what's the clear trend? The clear trend is that as the number of extracurricular hours increase, there's less people doing extracurricular hours that stretch all the way over there, right? It's a clear trend. But on this one, it's kind of odd because it looks like it's going up, down, up, down, up, down. This one is actually a case of showing too much information, right? Like it's too broken down. We're going from 0 to 2. That's just not all that useful, right? Like imagine if you were trying to sort people by height and you were like, all right, everyone who is from 5 feet to 5 feet 1 inches, go stand in that bin. And everyone who's from 5 feet 1 to 5 feet 2, go stand in that bin. That would just be like, you'd have too many categories. It's too much information. Instead, you'd probably want to go from like maybe 5 feet to 5 feet 6. Maybe you could go from 5 feet to 5 feet 3 inches, right? Something like that might be a little better. But if you broke it down by like 1 inch intervals, that's just too little and way too much information. On the other hand, if you said everybody that's from 4 feet to 8 feet, go stand over there, you're not going to get any usable data from that because that's almost everyone. It's not everyone, but it's almost everyone is going to be in that category there. All right, so we want to be careful with bin width. And in particular, this is important when we use Excel to make histograms, because when we use Excel to make histograms, right, Excel has its own random way of making the bins. And sometimes Excel will make bins that go from random numbers. So like, see how in this one, it kind of makes sense. It's going from 0, right? It's going from, hold on. See, in this one, it's going from 0 to 10, right? And then 10 to 20. That makes sense to our brains. Excel will do something like go from 0 to 2.75, and then go from 2.75 to 5.25. That doesn't make any sense in our brains, does it? Right? So you want to kind of make your bins. If you're displaying it, make your bins go to like whole numbers or at least like halves. So like you could go from, 0 to like maybe 5.5 or something if you needed to. But it doesn't make sense to go from like 0.395 to 0.42. That just makes no sense. So be careful of that as well. And in Excel will also sometimes give you really ridiculously small bins. instead of like normal size ones. So we said that histograms can tell us some information about the shape of a distribution. And here are some of the things we want to describe when we're talking about the shape of a distribution. So the first thing we want to describe is what we call modality, right? And modality, in this case when we're talking about it, we're looking at, does it have a single peak? Does it have multiple prominent peaks? Or does it have no peaks? So if it has a single peak, one place where it's just higher than everything else around it, like a hill, one hill, that's what we call unimodal, right? And when we have multiple different hills, that's what we call multimodal or bimodal. And when it's uniform, there's no particular hill, right? So what you want to do to try to visualize modality in the shape of the distribution is imagine that you have a piece of cooked spaghetti, right? And you're going to take that piece of cooked spaghetti and imagine it falling over top of your data set, of your histogram. And you're going to think, when I put that piece of spaghetti, that smooth piece of spaghetti over top of it, how many hills am I going to have? So in this first one, how many hills am I going to have in my spaghetti? Well, my spaghetti piece is going to go like this and then like this. So how many hills do we have? Just one. We only have one hill. So which one of these which word would we use to describe this first one? There's one prominent peak. What would we use?
Unimodal.
Unimodal, yes, unimodal. And for the second one, when we put our spaghetti over it, what's it gonna do? It's gonna go up, down, up. And how would we describe that one?
Multimodal.
Multimodal, or there's another word.
Bimodal.
Bimodal. So in particular, which one do you think would make more
Since
sense?
it's only two, I would say bimodal.
Bimodal.
But
Yes.
if you had a graph where you was all doing more than two, I would use the multimodal one.
Very good, Nakia. So that's exactly what the logic is. If it's only two, bimodal. If it's more than two, multimodal. What about this one? We'd be up here, down, up, down, up, down. What about that one?
Yeah, that's the multimodal.
Multimodal. Now, what about this last one? We go up.
Is it uniform?
This one would be uniform. So you could.
I would think uniform because you didn't quite make a hill like.
Yeah, exactly. So it's not like a hill. So yes, uniform. It's not like a hill. This would be more like if you went to the top of a mountain and it was like a plateau at the top of a mountain, right? Where, I mean, it could be not necessarily completely flat, but when you go up that mountain, you're not just gonna like fall off the other end right when you get to the top. You know, it's kind of flat at the top. So you see this one is kind of flat at the top when you get to the top, and it's a long time before it goes back down. So moving on, right, we have what we're describing as the shape, more descriptions of the shape of the distribution. And this time what we're going to describe is what we call skewness, right? So skewness, right, skewness is basically when we are looking at which way the histogram is leaning, right? Which way the data set is leaning. And it's a little counterintuitive because you're looking at it from the perspective of where the tail is, not from the perspective of where the body of the data set is. So in this first one, we would actually describe this as being right skewed. And the reason why we describe it as being right skewed is if you look at that arrow, you can see that the tail is leaning off to the right, right? This part, that's the tail, the part where it's kind of small, right? So it's leaning off to the right. How will we describe the next one? Which way is the tail?
Left.
It's to the left. So this one, the tail is to the left, right, which is over here. So it's left skewed. And then the last one goes up, goes down. Is there a tail?
No.
So there's no tail here. So imagine if I drew a line straight down the middle, both sides would kind of mirror each other, right? So it's symmetric. And now notice I said kind of mirror each other. Obviously, it's not an exact mirror, but it's much more mirrored than it is that there's like some random stuff just kind of stretched off and skewed to the side, right? So it's kind of symmetric. All right, so the last one will be symmetric. So we have right skewed for the first one. We have left skewed for the second one. And we have symmetric for the third one. When we have something that's symmetric, we can also call it bell-shaped. The reason why is it makes the shape of a bell. Or we can call it normal. So bell-shaped or normal. And these ones would be called skewed. Like just in general, they'd be called skewed, and then you say which way is the skew. Is it left skewed or right skewed? So we have a normal distribution, or we can have a skewed distribution. Remember, normal and bell-shaped are other names for symmetric. So moving on, we can also, from a histogram, and this is all from just visually representing quantitative data with a histogram. From a histogram, we can also identify some what we would call unusual observations or possible outliers. The reason why we say possible is because there is an actual test for whether or not something is an outlier. And if we haven't done the test, we can't say definitively if it's an outlier or not. So anywhere where we see a gap in the data set, that is a clue that there is a possible outlier. So in this case here, it's like we're going along, and then boom, gap. And then we got to pick up over here. So this gap here tells us that this is possibly an outlier. Same thing over here. All right, we're going along, and boom, we hit a gap with no data. Right? So that means that this is a possible outlier. So you can identify outliers like that by looking at gaps. So how could we describe the shape of this distribution? How could we describe this distribution? All right, so everybody take a pause for a second and think about it. Think about those different ways we could describe the shape. There were 2 different ways. And then come back and tell me how you would describe it. So if anybody's ready to describe it? Anybody want to give it a shot? You're on mute, Chanel.
I was gonna say right skewed, but then I noticed that it kind of, the information dies out towards the end, so now I'm not sure.
Okay, so we know it's not uniform because, we know it's not symmetric, right? Because it's just not symmetric. But remember,
I think it's right skewed.
it is right skewed. Yes, look at the tail. The tail is clearly over here. And there's another word. So this is describing skewness. What's the other thing we need to describe? Starts with an M.
Multi, or no?
Modality.
Oh, modality, yeah.
And how will we describe the modality for this data set, for this histogram? How would we describe the modality?
Una?
Yes, very good. Unimodal. Why is it unimodal? When we did our limp noodle test, right? There's only one peak.
Just one peak.
Just one peak right over there on the left side of the thing. Only one peak. So we would say that this was right skewed and unimodal. Right? And there you go right there. And we have a possible outlier that's all the way over here. That's a possible outlier. Right? Because we have this gap right here. And if we look at that number doesn't even make sense. How are you spending 70 hours a week on extracurricular activities? If you are spending 70 hours a week on extracurricular activities, that's not extracurricular. That's just your job. You work in a job. That's no longer extracurricular. This has become your job. So moving on, here's some just a little kind of quick, maybe a refresher, maybe like a quick study tool type of thing. These are the different shapes for modality, and these are the different shapes for skewness. This is for when you do your noodle test. This is helping you do your noodle test, you see what shape it's looking like, right? So we go back, right? We can clearly see what kind of shape this is, right? There's one peak, so it's fitting here for unimodal, and it was fitting here for right skew. So this is kind of like a study tool to help you remember all of the different ones. So let's look at this one. Which of these variables do you expect to be uniformly distributed? A, the weights of adult females. B, the salaries of random sample of people from North Carolina. C, house prices. Or D, birthdays of classmates. Remember, uniform.
C.
So somebody said C. Remember, uniform is what? What does it mean for it to be uniform? What is that shape? So if we were to draw a histogram, we're basically saying that the histogram is going to look.
There's not a particular peak.
There's
Oh,
no,
that's right. You
no
said
slope.
it's saying
It's-
ununiformity. I'm sorry, I thought you said uniform. Okay.
That's uniform, right? There's no peak, right? There's no slope. It's just kind of all of them are kind of in the same place. Do you expect, and remember, each of these represents categories, so we could actually fill in some categories here, right? Let's look at A first. For A, the weights of adults, females, what kind of categories would we break the weights of people into? Like we would go from like what?
Small, medium, and large.
Yeah, but I'm saying if we use numbers, maybe we go by 10 pounds or 20 pounds. We'll go 110 to 130,
Oh, okay.
130 to 150. You go 150 to 170, 170 to 190, so on and so forth. Do you expect the number of people in each of these categories to be the same?
No.
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 Because there's like some middle point that most people are going to be at, right? There are probably less people that weigh 110 than there are that weigh 150, 160 or whatever, right? That just makes sense. So we can say it's not the weights of adult females. We can do a similar thing with the other categories. What about salaries of a random sample of people from North Carolina? How would we expect those to be? We could do same kind of things. We could go 50,000, 40,000. Let's go 40,000, 50,000, 60,000, 70,000, ... Do you expect all of those, the number of people in all? So like all the way up here would be 80, 90, 100, 110. Do you expect all of these categories to be the same?
No.
No. So that would be another one.
That'll be another one. No, because if you look at it, I mean, they're going to be there's some middle point, right? They're going to be less people that make $110,000 a year in North Carolina than make, say, $50,000 a year in North Carolina. They're just going to be less, right? So we can say it's not that. You all do that same logic with house prices. Do you expect house prices to be uniform?
Yes.
No. No.
If we made these categories, are all the house prices going to be spread out evenly?
No.
No, they're not, because you're not going to find the same number of, $2 million homes as, $100,000, $200,000 homes. You're just not going to find the same number. It's not going to be spread out evenly, right? They're going to be more at some middle area. So what about the birthdays of classmates, like the day of the month?
Yes.
To be uniform.
Mm-hmm.
So yeah, it is birthdays, because if you think about it, there's nothing that makes you more likely to be born on a particular day than another day, right? And if you took a whole bunch of people, I mean, some of the people who's going to be born early in the month. Some people are going to be born in the middle of the month. Some people are going to be born at the end of the month, right? Is there anything that makes you more likely to be born in the beginning of the month than in the middle of the month? Not that I know of. I mean, maybe if you're like deep into some kind of astrology or something, you got some kind of theory of why people are more likely to be born in the middle of the month. I don't know. Maybe you're like, Venus is rising after this date, so people are going to be born. I don't know. But nothing that we know makes people more likely to be born in the middle of the month, right? So it is actually going to be birthdays. Birthdays are more likely to be uniformly distributed, right?
What
So
if you use like the COVID situation?
a what situation?
The COVID, the pandemic, so you can kind of guess.
So that
When-
might be if you say people are more likely to be born in a certain month, and yes, you
Oh,
do
yeah.
actually find that people are more likely to be born in certain months. You can track baby births to like when wedding season is big, because you know that people have a wedding, then they have a honeymoon, and then you know everybody is adults here.
Valentine's,
So
get more
Valentine's Day,
Scorpios.
right? Yep, that's a time. Winter, because you're stuck inside. Christmas, you know, you're inside. It's cold. What else are you gonna do? So yeah, these things make it more likely that the month someone's born in, right? There are more people born in certain months than other months. But for the day, that's not so likely, right? Because I mean, even your due date might be the 15th, and you might have that baby on the 1st, or your due date might be the 15th, and you had that baby on the 31st, right? That is even up in the air. So, yeah, it's definitely going to be birthdays. This is a little bit about how to actually go ahead, like to technically create a histogram. You can read through this in depth. It's just like, and it has an example of taking, see all these numbers here, taking these numbers, making a histogram with these numbers, like actually doing it, and how you actually go about making a histogram. There is an actual technique. For the most part, though, we're going to make our histograms in Excel. That's what we're going to use. We're going to make histograms in Excel. The main thing you need to know about making histograms is that all of your bins, right, they all need to be the same size. That's the important part. So you can't be like, okay, one bin is going to go from 0 to 10, and the next one's going to go from 10 to 15, because we did a size of 10 for the first one and a size of 5 for the second one. They all need to be the same size. That's the main thing. Outside of them all being the same size, there are not really any other rules besides them all being the same size. We can also have a relative frequency histogram, which is basically where we have a histogram, but instead of counting how many people were in that particular bin, we're instead counting what percentage of the people were in that bin. So just like we did the relative frequency table, right? We can do the same thing with a histogram, where we just count percentages. So if there are 100 people in total and you have 5 people in a bin, then you're going to go up to 5% or 0.05, right? If there are 20 people in the bin, you're going to go up to 0.2, because that's 20%, right? So that would be a relative frequency histogram. But again, this is here for your reading pleasure, right? I would recommend that you just read it, kind of follow it along. It's not very difficult, but again, we will be making histograms in Excel. The last thing we're going to talk about is what we call deceptive graphs. And you need to be mindful of this, because our goal is always to be very clear and straightforward without graphs. And if you remember, there was a scenario we talked about in the first day where we had a deceptive graph, right? And that graph was deceptive because they did what? They didn't keep the order and the structure the same, right? What did they do? They switched around the order of the graphs, right? They moved the bars relative to each other, and that's what made that graph deceptive. So there are two main types of deceptive graphs we will speak about. One of them is a non-zero vertical axis, and the other is a pictograph. So with a non-zero vertical axis, here we have two scenarios. And if we look at this first one, and I asked you, right, we did this experiment, and we were looking at what percent of people experienced nausea. Would you say a whole lot more people experienced nausea when they took Oxycontin versus when they took the placebo?
Yes.
Yes.
It looks like a whole
Yes.
lot, right?
I mean, yeah, it looks like it.
Like how many times more would you say? Don't look at the numbers, just look at the picture. How many times more would you say?
10.
10 times more? Okay, that's a good guess. About 10 times more. That's kind of what it looks like. Like 10 of these would make one of these. Right? That's kind of what it looks like. But notice something. What did we start this graph at? Did we start it at 0?
No, they started
No,
at
10%.
10%.
We started at 10%. So if we started at 10%, what is the percentage for the placebo?
That's like 15.
Nope, look at the placebo.
I'm sorry. 11?
Like
About
what-
11%.
Yeah.
about-
And what's the percentage for the Oxycontin? About
23.
About 23%.
23. Yeah.
Is 23 10 times 11?
No.
No,
No.
that's more like 2 times 11, right?
Mm-hmm.
But you see how the graph made it look like it was 10 times it, but it's
Deceptive.
not. It's 2 times it. It's deceptive. When we actually make it start at 0, see how the whole picture changed when it starts at 0? When it started at 0, now it actually looks like the placebo was half of the placebo. Is a fly in here. The placebo was half of the Oxycontin, right? So that is an example of a deceptive graph. Long story short, when we don't start at 0, right, we are exaggerating the differences between things when we don't start at 0. And we don't want to do that. We want to always start our graphs at 0. Funny thing is, Excel will sometimes not start your graphs at 0. And you need to go in and double check and make sure it's starting your graph at 0. Excel will do it, Google Sheets will do it. Pick the graph as another example. So here it says in the bottom, 37% in 1970, 37% of U.S. adults smoked, and in 2013, 18% of U.S. adults smoked. Don't that 1970 cigarette look so much bigger than that 2013 cigarette? Like, so much bigger?
Yes.
Yeah.
But how does that cigarette represent 37%, but the other cigarette represents 18%? Like, who made that up? What is it based on?
It's just a picture.
It's just a picture. It's based on nothing. They just took a picture of a cigarette, blew it up for the first one, and shrunk it down for the second one. That's literally all they did, right? And so when you put a picture in there like that, since the size that might not actually correspond to the numbers, right, is kind of deceiving, right? Since the size doesn't correspond to the numbers. And people will do that often because they know the way our brains work. The way our brains work, you'll just see a big cigarette and a little cigarette, and you'll be like, whoa, 1970 was so much smaller, so much bigger than 2013. That's what you'll say, right? So you want to be careful. There's some other ways to be deceptive with graphs, but these are the main ones that we kind of want to, keep in mind. These are the main ones. So with that, we are almost done. I was about to say we are done. We are almost done. Very last thing, here's just some very quick tips on making a graph. So for example, if you have a very small data set, you probably shouldn't use a graph. You should just use a table. So if you have a small data set, you maybe shouldn't make a histogram. Maybe you should just make some kind of frequency distribution table or something like that. And the other ones are just about, not using a bunch of catchy decorative stuff. Just keep it simple and straightforward, right? Don't distort the data that you have. And this last one, almost all ink, that's kind of a remnant of the time where you were drawing graphs. But the same idea is for a computer. If you're putting a graph in a paper, you don't want to bedazzle your graph. You don't want to decorate it up nice. Just keep the graph being a graph. Let the graph speak for itself. Let the data in the graph speak for itself. So that's basically what we're saying here. And with that, we are finished for today.